Okay, welcome back to the Signals and Systems class. My name is Jong Park, and I am with the Department of Military Digital Convergence. In the previous lecture, we talked about the Laplace transform and entered the chapter which is about the properties of the Laplace transform and also the second order system. The chapter's title is second order system, but we mainly focused on the properties of the Laplace transform in the previous lecture. So this was just a review of the preliminary stuff, and we went over the properties which include linearity, of course, and the derivative. And if S equals to j omega, then we witness the same property with respect to the derivative or the differentiation. And also the convolution is expressed as multiplication in the Laplace transform, which is the very same thing that we studied in the Fourier transform. So it's a generalization of the Fourier transform, and this h of s is called the system function, whereas it was frequency response in the Fourier transform. And the region of convergence is highly related to the location of poles, right? And the region of convergence is very important with respect to the stability of the system. So this is a very important logic flow, which is that when we studied about the LTI system, that if the impulse response is absolutely integrable, then the system was stable. And on the other hand, when we studied the Fourier transform, there was a condition called Dirichlet condition, which is about the convergence of the Fourier transform, and this was related to the this was also related to the absolute integrable of the system. Therefore, we can conclude that Fourier transform's convergence is related to the system stability. With respect to this Fourier transform in Laplace transform, then the Fourier transform only represents the j omega axis, which is the imaginary axis, and therefore if ROC includes this imaginary axis, then we can say that the Fourier transform converges, the Fourier transform of the corresponding signal converges, and that means the system is stable. And moreover, if system is causal, just like for many physical system, then it is absolutely right-sided time function. And if that happens, we know that the region of convergence is to the right of the rightmost pole. Oh, I'm sorry about the typo here. And we know that when we talked about this region of convergence in the previous chapter. So if it's right-sided, then the ROC is to the right of the rightmost pole. And therefore, to include this Fourier transform sector, then all poles should be on the left half plane, because ROC is to the right of the rightmost pole, and it must include the imaginary axis of the S-plane. And we ended up the same conclusion with respect to the inverse Laplace transform. If we assume that we are dealing with the LTI system, then we definitely can represent the impulse response Laplace transform as a fraction like this. And denominator as well as numerator consists of the polynomial, and we can do the partial fraction expansion to like separate them, like in a linear combination of S minus pole. And if we perform the Laplace transform, then this Ki is decided by the zero locations and initial conditions, and this Pi here is a pole. Therefore, if time increases, this exponential must decrease for this h of t to be stable, which means it converges to 0. And this happens when the real part of pole, which is sigma, is negative. And therefore, we can end up the same conclusion that all poles must be on the left half plane, right? So with different perspective, same conclusion. Stability means that all poles must locate in the left half plane. And there is a system which is unstable. That means the pole is on the right half plane, and if the pole is on the right half plane like this, then the system itself is unstable, right? It's an unstable system. And what the controllers do is that you augment this open loop system with the closed loop of some controller, such as PID controller, to have a closed loop, and now the overall system becomes this system, and this is the input, and this will be the output of the overall closed loop system. And by using this feedback system, you can take these poles to the left hand side. This is what the controllers do. Control engineers do is that if we're dealing with the LTI system, then it can be represented by the poles and zeros, the system function. And if you have an unstable system, which means you have poles on the right hand side, and by using this controller, you will locate the original pole to the left. And also, even though you have a stable system, which means all poles are located on the left hand side, you can use your controller, compensator or PID controller for the classical control method. You can accelerate or improve the performance of the system by using the controller, even though it's already stable. Okay, but we are not in the control lecture. We are in the signals and systems lecture, so that was just a slight digression. However, it's really good to know for you to study more about the controller based on your signals and systems. Actually, the things that you learn in the signals and systems course, like the Laplace transform and the Fourier transform, they are the basis of the classical control lecture. So you will learn such as PID controller and compensator, such as the lag compensator or lead compensator in the classical control lecture. So if you are interested, then like after having this course, maybe in the next semester you can try the classical control, which is based on the things that we do in this current lecture. Okay, thank you. And okay, so back to our content. That now I would like to use the Laplace transform properties to apply it to the differential equation. So the derivative of yt with respect to time plus a times yt equals xt. This is the standard first order differential equation. And we perform the Laplace transform for this equation by using the derivative property and the linearity property. So we use the Laplace transform, we use the derivative property and the linearity property. So if we do that, the derivative becomes s times the Laplace transform itself and plus a ys equaling x of s, like this. And since I want to obtain the system function, or rather I can say I want to isolate the y-axis. If I do a math, then it will be like this, right? So ys equals 1 over s plus a times x of s. And if you compare to the convolution property of the LTI system, we will recognize this as a system function, right? So this right here, 1 over s plus a, is the system function. And we know this by the convolution property. Right? So this simple first order system has one pole, right? We can describe that this system has no zero and only one pole. At s being minus a. Alright? And if I want to obtain the impulse response in time domain, then you should do the inverse Laplace transform, right? Because this impulse response is the system function if you perform the Laplace transform. So if you want to reverse, if you want to obtain the y of t, then you should do the inverse Laplace transform, right? So we know that this is 1 over s plus a. So by inverse Laplace transform, this h of t can be obtained. But as a matter of fact, that as we experienced, there could be multiple answers depending on the region of convergence in the Laplace transform, which is very unique for the Laplace transform. That was because we have an additional variable, this sigma, right? And for this, the simple equation with a simple problem that if the region of convergence is, if it's bigger than minus a, so the pole will be our boundary, right? And if the region of convergence, which means the real part of the S, is bigger than minus a, then you will have e to the minus at times the unit step function. You know that this becomes 1 over s plus a with the Laplace transform with this kind of convergence, region of convergence. However, the answer will be minus e to the minus at times the reverse of this unit step function if you have the different ROC. Like this. And you know that if system is causal, then this will be your pick, right? And you know the reason. And if system is not causal, then the second one will be your pick. What I'm trying to say is that your final answer depends on the additional information, such as the stability, causality, such those things, okay? The representative to the additional information will be stability and causality. So for the problem, maybe the ROC is provided in the problem statement, and you may choose your final answer from multiple candidates by that ROC. However, in real problem, those ROC are not provided, so you can choose your answer of the inverse Laplace transform with this kind of practical information. If the system is stable, then you have the additional information of that. If you have the causality, which is true for the physical systems, then of course you can choose your final answer based on this information. So what I'm trying to tell you is that the linear constant coefficient differential equation can provide you the algebraic expression for the system function. However, with only having this algebraic equation expression, you cannot choose the region of convergence. So definitely you need the additional information like this. Okay, so additional information such as stability, causality, or etc. will give you the choice of ROC. And if you have the condition of this stability, that means ROC should include the imaginary axis, right? And if you have the condition of the causality, then the ROC is to the right of the rightmost pole. Remember? These are the additional information, or these are also called the auxiliary information. In the Fourier transform, when Fourier transform was used as a application to the differential equation, we haven't talked about this auxiliary information. However, you have to choose the region of convergence for this Laplace transform. Therefore, you need this kind of additional information. And the two most representative examples are these stability and causality. Okay, so I think we can move on to our next subsection, which is the second order system. The second order system here is very popular because many of the systems in real life can be represented by the second order system or the combination of the second order system. The most important example for the second order system is a spring mass damped mechanical system. You know that you have a mass, and I think you have seen a lot of picture like this. So you have a spring like this, and you have a mass, which is a rigid body, and you have a damper, like this kind of stuff. So this is like the most popular second order system. It's a mechanical system, and your displacement of this rigid body is represented by the second order system. So I would like to introduce the standard form of the second order system in time domain. It's a second order, therefore you So you have like the second derivative, therefore you have the second derivative of yt over with respect to time plus 2. Let me show you just the full standard, and then we will discuss about the notations here. Okay, so this is our standard form of the second order system in time domain, and this notation here is called zeta, and this is a Greek letter. And this omega n here, which frequently appears, this is called the omega, and this is also a Greek letter. It's really similar to the W in alphabet, however it's an omega. And many of you may question why these are introduced here, but with the derivation and with the explanation, we will explain what these variables mean in the near future. Okay, so at this very moment, just adopt this form, and we will do the Laplace transform and go on, and then I will show you what these parameters mean. Okay, so what do you want to do if we see the differential equation? We would like to apply the Laplace transform. And if we do that, so it's our first time having the second derivative. So it's a second derivative, therefore you will have to multiply ys by s squared, right? So s squared times ys plus, these are all constants. Therefore they are not affected by this Laplace transform. So 2 times zeta omega n. And we have to apply the Laplace transform for the first derivative also. Therefore, you will have s times y of s, with the omega n squared times y of s equals, this is also a constant. Therefore, you will have this kind of Laplace transform result. And I can combine all the others except ys like this. So this is the beauty of the Laplace transform. And recall that the system function is in this relation. Therefore, if you compare this equation to this one, then we know that h of s of the second order system will be omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This will be your second order system in Laplace transform. We can immediately find out that you have no zeros, right? You have no zero. And how many poles do you have? You have 2 poles, right? Because you have second order polynomial in the denominator. And if I can express this h of s like s minus c1 maybe times s minus c2, then I will have C1 and C2 as the system's pole, right? Therefore, I can obtain the C1 and C2 by using the solution for the second order polynomial. And if I do that, then I will get minus zeta omega n plus omega n square root of zeta squared minus 1. And you will get the second one for this one. So these are the poles of our second order system. And I will change my page because I ran out of this place. Okay, so for the first case, let's assume that so let's assume, let's assume first that zeta is, the value of the zeta exists between 0 and 1. Okay, then with this boundary, can you see what happens inside this square root? This square root, inside the square root will be a negative, right? Therefore, this whole thing will be the imaginary number. And moreover, you can find out that you have the same real part and the different imaginary part with the reverse sign. Therefore, these two are complex conjugate to each other. So C1 is a complex conjugate of the other one, which can be expressed as the same minus zeta omega n plus j times omega n times 1 minus zeta 1, zeta squared, like this. If zeta is smaller, if the positive zeta is smaller than 1, I can express like this. I express the relationship of C1 and C2 like this because they are complex conjugate to each other. The meaning of the complex conjugate is that you have the same real part, however, you have your sign of the imaginary part is reversed, is opposite. Okay? And if you locate your poles, your two poles, when you have this this condition in the S domain, then it will be like this. As always, this is a real value and this is the imaginary value, and you have the same real part Therefore, you will have minus zeta omega n here. And for the imaginary part, C1 has the positive one, so this is omega n square root of 1 minus zeta squared. So this is the first pole, and we have to mark that as x because we agreed to that. And the second pole only is different from the first pole with the imaginary part. So you will have the same but different. You have the same real part, however, the different imaginary part like this. So I'm sorry for this confusion. It will be minus here, and you will have these two poles when your zeta is bigger than 0 but smaller than plus 1. Okay, I can characterize some things about these two poles, okay? First, what is the length from the pole to the origin for both? What's the length of this from the origin to the pole for both one? If you do the math, then this length will be omega n. And also, if you set this angle as theta, then what happens is that the sine theta will be zeta, because this is omega n, and this right here will be zeta times omega. So this over this will be zeta, which corresponds to the sine of theta. And I've already said that the pole is symmetric with respect to the x-axis, and that's because you have the same real part value, however different, two imaginary parts. And what happens to these two poles if I fix omega n but control this zeta between 0 and 1? What happens? Since this omega n is fixed, the trajectory will be on the circle, right? They will be on the circle because omega n is fixed. And these two poles will be on the real axis when zeta is 1. Right? Because if zeta is 1, 1 minus 1 is 0, so this part will go to this part, and you will have, if you think of this circle here, by meaning that omega n is fixed, then you will locate at this part. What happens if zeta is 0? If zeta is 0, this part becomes 0, which means the poles will be located on the imaginary axis. So poles are located in these two complex numbers when you have this boundary. And what happens if zeta is bigger than 1? If zeta is bigger than 1, then you have the positive value inside this square root, right? So this will be the real value, and this also will be your real value, which means C1 and C2 are both real. That means your two poles are both located on the real axis, and this will be your standard, and from that standard you will have your first pole increased by this amount and your second pole decreased by the same amount. So it will be like this will be your minus zeta omega, and maybe you have pole here and pole here, which is the same amount, okay? So maybe I can say that this much will be omega n square root of zeta squared minus 1, and this is also the same amount. So, but actually, we are more interested in the first case where poles are complex. If you have poles on the real axis, then it means there is no oscillation when you convert this into the time domain. If you have the complex number, then there exists the oscillatory motion, which means there is a vibration with respect to time. So to summarize, the first case, if zeta is bigger than 0 but smaller than 1, this is called underdamped type. And if zeta equals 1, then you say that it's critically damped. And if zeta is bigger than 1, which is our second case, this is called the overdamped. So this second case, there's no oscillation. And with this underdamped type, which is our interest, where the poles are located on the complex numbers, then this will be you have the oscillation with respect to time. So if you have no oscillation, then it means that system is well damped. So now it's our time to introduce our two specifications. So zeta is called the damping ratio, the amount of damper that exists in the system, and the omega n is called the natural frequency. is the natural frequency of that system. Okay, then what about the first order system? We introduced directly the second order system, but what about the first order system? Does the first order system have the thing that is called damping ratio or natural frequency, this kind of stuff? So I will talk briefly about the first order system and then continue with our second order system. So the first order system so this is a slight digression, but I already mentioned, so I will introduce briefly about the first order system. First order system can be represented as follows. So the system function of first order system has no zero and has only one pole, like this. You have one pole, therefore it's a first order system. And if you make this part to 1, that means you will divide both sides by A0. And it'll be B0 over A0 and S over A0 plus 1. And we introduced tau as the time constant of the first order system. So tau, which is 1 over A0, is called the time constant. So this tau is the only term that describes the first order system, whereas you have two variables regarding the second order system. Therefore, the pole of your first order system is located at minus 1 over tau, right? And this time constant, so in time domain, so now we are in time domain, and if this first order system is stable, then it will decrease like this. So if our initial condition is 1, then if you reach tau, if t is tau, then if I may think this here is the point where the t becomes tau, then at that time constant, your output will decrease to e to the minus 1, which is approximately 0.368. Which means, so the meaning of this first, the meaning of this time constant in first order system, that is that the first order system, the stable first order system, decays and meets the point of approximately 36.8% of the initial value. When, I'm sorry about this period, when t equals tau. So this is the meaning of your the term tau, the time constant. And if some system is modeled as the first order system, and by asking you the time constant, then you will know the speed of that system. If time constant is small, that means the system decays faster, right? Whereas if the time constant is big, that means you have to spend a lot of time decaying, a lot of time converge to zero. So with your time constant, by asking someone about the some system's time constant, then you will have a certain amount of feeling about the speed of this first order system. Okay, so this was a brief introduction about the first order system, and I would like to conclude that you have only one term for your first order system. Now let's go back to the second order system where we have two specifications. So I would like to draw the frequency response that we did during the Fourier transform for our second order system. And we will consider our zeta being smaller than 1, as I told that this is our stuff here. So obtaining frequency response is equivalent to having the Fourier transform of the impulse response, right? So frequency response is related to the Fourier transform of impulse response. And that means in terms of Laplace transform, the S should be restricted to the imaginary axis. Which means S must be set as J omega, not sigma plus J omega. Therefore, if I have H of S as omega n squared over S minus C1 times S minus C2, where C1 and C2 are these, right? I have to set S as j omega like this, which means it'll become omega n squared j omega minus c1 j omega minus c2. So this is the Fourier transform of our second order system. And do you remember that we have to consider not only magnitude but phase for your frequency response? So okay. So to obtain the magnitude and phase, we would like to use the polar form. So that's the advantage of polar form. And if h of j omega is expressed as similar to this one, maybe for the general point of view, if I say if h of omega is S will be confusing you. So if it consists of B1 times B2 times B3 like this, B1 over B2 B3 like this, then we can represent each B's in polar form. And if you do that, then it'll be maybe like R as the magnitude and theta as the phase. Then I can express this as R1 times e to the j theta 1 and R2 times e to the j theta 2 and the similar one to the third one. And the beauty of this polar form is that I can combine this magnitude because they are all related with this multiplication or division. And also I can combine these phase like this, e to the j theta 1 minus theta 2 minus theta 3. So what I'm trying to say here is that you can obtain magnitude and phase easily by using the polar form. So the magnitude can be obtained by just multiplying all of the magnitudes of the denominator and divide them by the multiplication of the numerator. The magnitudes of the denominator, numerator divided by the denominator, and with a phase, what you have to do is you have to, in this case, do the summation for all of the phase of the numerator and subtract that by all the phase of the denominator like this. So you can easily obtain magnitude and phase by by using this polar form. And so back to this form, so if h of j omega is in this kind of form, then like the obtaining, like obtain this magnitude, for example, the thing that we have to do is you have to divide the magnitude of the terms in the denominator by, numerator by the denominators, right? Therefore, the magnitude can be expressed by this vertical line. And this is like dividing omega n squared. So you don't have a parameter here, right? You don't have the, so omega, h is the function of omega. So this omega n is just a constant, and this should be divided by magnitude of the first term and the magnitude of the second term. So this means that, so we are talking about this complex case here. And if this j omega is this vector, j omega, then this j omega minus c1, let's refer that this is c1 here, and this is c2 here. And this j omega minus c will be this vector. It starts from the c1 and points to the j omega. This will be our j omega minus c. And this will be j omega minus c2. So to obtain magnitude at this point, it means you have to obtain the length or the magnitude of this vector and the length of this vector. And you have to divide omega n squared by them both. So this is the interpretation with this S-plane. And for example, if C1 is minus zeta omega n plus j omega n times square root of 1 minus zeta squared, then this j omega minus C1, I'm talking about this one term here. That will be like J omega plus this term. What I did was just put J omega here and subtract C1 from J omega. And this will be like zeta omega n as the real part, and the imaginary part will be J minus J of omega minus omega n times the square root. Therefore, to obtain this with this rectangular form, to obtain the magnitude, you will have to do the square root of the real part squared the imaginary part, like this. And this here is the only parameter, because we are varying the omega here through this imaginary axis to find out these length for the magnitude. Okay, so I mean, if J omega is here, you have to divide omega n squared by this length and this length. That's what I wanted to tell you. And if you want to express this term here with the actual function, then you have to go this process to make the magnitude from the rectangular form. So this is the only variable here. These are all constant, which is decided by the system. It's a system specification. So if I draw this magnitude for this second order system, then it'll be like this term. So this is the magnitude of, this is the magnitude. And since we're talking about the frequency response, you can witness that the x-axis is the frequency. Okay, so I would like to compare this plot, this S-domain plot, with this result of the magnitude. So let's see what happens when omega goes to infinity or minus infinity. If omega goes to infinity, then you have to measure, like if omega is here, then you have to measure this vector and this vector. And these two long magnitudes will be placed on the denominator, where you have a constant numerator, right? So as omega changes, the value of the numerator does not change. However, the denominator varies, right? Therefore, it's obviously true that this magnitude gets smaller and smaller as omega gets bigger and bigger. And see what happens when does this J omega minus C1 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 when does this J gets the smallest? When you have omega here, right? So this is the part where you have the smallest value of the length of this vector. And that means you will have the biggest. You will have the biggest magnitude at that point because you have the smallest one on the denominator, which means you have the biggest value here. So you will have a peak or a resonance at that point, which is 1 and minus 1. 1 for this value and minus 1 for this value here. And omega should be 1 because this imaginary part so omega must be 1 because I'm sorry, omega must equal omega n, right? And in this case, it is 1 because we set omega n as 1. This is my bad. So because we should oh, I'm very sorry. So okay, so one more time. With this relationship, you will have omega n square root of 1 minus zeta squared as this value here, right? So if you want to get a parallel value, then this value should be omega n 1 minus zeta squared. At this point, with the specified omega n and zeta, this value will become the smallest, right? And that point where you will experience a peak, and this peak will be different with respect to the zeta and also the omega. And in this figure, you fix the omega n and you compare the zetas. But I think we will continue the interpretation of this figure in the next lecture, okay? Sorry for the confusion at the very last part of this lecture. And if you have any questions about the second order system or also the first order system, please let me know. And also think about this applying the Laplace transform in the differentiation equation, and the things that I talked about, the additional information which is needed to have the inverse Laplace transform. Okay, and also you need to distinguish the situation which depends on the value of this zeta, and think about these new words here, which represents the second order specification. Okay, I think that's it for today, and thank you very much for your attention.